So good afternoon. I'll be presenting Buildroot, a tool that helps building embedded Linux systems in an easy way, and also probably one of the projects that is the ugliest logo possible. But that's not really the point. Before we get started, a quick poll. Who in the room is either working or playing with embedded Linux? Yeah, so a good number of people, like more than half of the room. Okay, great. So first, who am I? In a quick few words, I'm the CTO and embedded Linux engineer in a company called Free Electrons. We do embedded Linux stuff, both development and consulting and training. We have a strong open source focus, so we contribute to the Linux kernel, for example, to Buildroot. And we also release all our training materials under a Creative Commons license, so we have lots of embedded Linux and Linux kernel training course material freely available for everyone to download. I am an open source contributor. I contribute to the Linux kernel, especially on the ARM support for certain processors, namely the ones from Marvell. And I'm also a major contributor to Buildroot with, in fact, not 1600 but 1900 patches contributed since the last few years. And I come from Toulouse in France, so quite far away, and you've probably noticed my terrible accent. So embedded, these days when people say embedded, usually they think something like that, like phones, tablets, consumer-grade devices. And those devices, they typically have very powerful CPUs, lots of RAM, lots of storage, a full-feature general-purpose operating system, usually Android, but it can be something else, but something with like many applications that you can install, remove, upgrade, and so on. So really a complete desktop operating system. But in fact, embedded is much more than just the devices that you have in your pocket. We have embedded systems in like laser cutting machines, point-of-sale terminals, agricultural machines, windmills, and many other systems that you may never have heard of. And those systems are much more application-specific, so they need a more custom Linux system that may need to boot fast or meet some real-time deadlines or have other types of constraints. They usually have a lot less powerful CPUs. Typically, like in a few hundreds of megahertz is quite common in those systems. They may use like specialized CPU architectures, so there's much more than x86 and ARM in the embedded world. MIPS, PowerPC, of course, but also like Blackfin, Microblaze, NIOS, and other bizarre architectures you've probably never heard of. Those systems have also less RAM, less storage, and a long lifetime and maintenance period. So the constraints are quite different than the ones that we have in consumer-grade devices such as phones and tablets. And so the way we're going to create the Linux systems for those two types of embedded systems might be a little bit different, as we're going to see. So to build an embedded Linux system to like integrate all the different components that make a Linux system, the init system, the graphical stack, and the network processes, and so on, there are different solutions that are available. The first thing that every one of us do is use binary Linux distributions, Debian, Ubuntu, or more specialized one like Raspbian for Raspberry Pi or other distributions. So those are pre-built. So what you get are binaries that have been compiled by other people. So the good thing is that it's readily available, it's easy to install, easy to use, but it's quite large, it's not available for all architectures. It's not necessarily very easy to customize. So of course you can install and remove packages, but if you want to like slightly adjust the config of one package or rebuild the entire thing with different compiler options, it's a little bit tricky. And it generally requires native compilation. So if any one of you have tried to build a Linux kernel on a Raspberry Pi, it takes a long, long while. So native compilation is certainly nice for some things, but for some other things it's not so nice. So the other approach is the other side of the spectrum is to build everything manually. So from scratch, you take the source code for every component in your system, take the tarball, configure it, build it, install it, and do all of that stuff. But it's quite hard because you are going to face cross-compilation issues. You'll have to face the resolution of the dependency tree. And in the open source world, we reuse a lot of things, so there are many libraries. It's not reproducible unless you take very clear notes of what you've done, and you don't benefit from other people's work. So there's kind of an intermediate solution that sits in between. And of course, as you might have guessed, Buildroot fits in that intermediate solution. This intermediate solution is the usage of tools that automate the process of building a Linux system from scratch, from source code, all the way to a completely working system. So since we build from source, we can customize as we want. We can build very small and flexible systems, so we can just have what we need inside the system and nothing more. It makes the process reproducible because we have a tool instead of just a bunch of command lines that we run. The tool handles the cross-compilation and dependency issues. It's visually available for all architectures. We're going to see which ones Buildroot support. But of course, it's one tool to learn, and you have to, well, spend some time waiting for the build to finish, but at least you're not involved into that, so you can drink some coffee or other nice drinks while the build is going on. So the principle of those tools is, there are many tools in this, well, area, but the principle of all of those tools is more or less the same. Basically, they take some source code, either from open source components or in-house components, from their Git trees or tarbals on the web. And they are going to produce at the end a root file system image that contains all your application and libraries and init scripts and config files and so on. Possibly a kernel image, a bootloader image, and a cross-compilation toolchain. And you're going to feed into this tool a configuration that says, for my system, I'm going to build it for ARM, and I want this graphical library to be inside, and this networking application, and so on and so on. So as I said, you build from source, so you have lots of flexibility. You can adjust whatever configuration option for each individual component as you want. Since we're cross-compiling everything, we are leveraging the power of our fast desktop and server machines, so you can like have a big Intel machine to do all your cross-compilation, which allows you to build a kernel for your Raspberry Pi in just a few minutes instead of a few hours if you do native compilation on the target. And those tools have recipes for building components, so it makes it easy. Instead of having to worry about how to compile x.org, you just select an option and it's gonna do it for you because the tool knows how to build x.org. So there's a wide range of tools available to do that. Yocto and OpenEmbedded, PTXDist, Buildroot, LTIB, OpenBricks, OpenWRT, and much more that I've probably forgot. But from what I can see, but of course I have a biased opinion here, I think two solutions are really emerging as the most popular ones. On one side, there is Yocto and OpenEmbedded. What those tools allow is to build a complete Linux distribution with binary packages. So it produces like your own custom Debian for you. And then from this set of packages, you can create embedded Linux systems that are able to upgrade, install, remove applications through binary packages as you normally do in a binary distribution. Those tools are very powerful, but they are somewhat complex and have a quite steep learning curve. So if you want to invest quite some time, they are certainly nice. Buildroot is kind of the opposite side of the spectrum. It simply builds a root file system image. There's no binary packages. You can't like install, upgrade, remove things. If you want to change something, you have to go back into the tool, adjust your configuration, and recreate a new root file system image, which is perfectly fine for most of the embedded Linux systems that are used in the industrial space. And it's also a tool that's much, much simpler to use, understand, and modify, as we're going to see throughout the presentation. So in just a few words, what are the main characteristics of Buildroot? It's a tool that can build a toolchain, a root file system, a kernel, a bootloader. It's an embedded Linux build system. It's easy to configure because it uses a miniconfig, xconfig, nconfig, gconfig interface, just like the Linux kernel itself. So if you've ever built a Linux kernel, you already know the configuration interface for Buildroot. It's fast. You can build a simple root file system in just a few minutes, so you don't have to wait for hours. It's very easy to understand because it's written in Make and it has pretty good documentation. Of course, it could be better, but we have good documentation, I believe. The default file system that it builds, it weighs 2 megabytes. So it's, when I say small, I really mean small. So it just contains small C library, and which is uclibc and BusyBox, and that's all. And then you can add more stuff on top of it, but at least you start with something small. It has more than 1,000 packages available, so you can just select things and you don't have to worry about how to actually compile it. And there are many architectures supported. It uses well-known technologies. As I've said, it's based on Make, so it's entirely written in Make files. And it uses kconfig for the configuration interface. So any like kernel developer or Linux developer in general knows those technology already. It's also a vendor-neutral tool, so it's not like one single company behind the tool doing the development or driving the directions. It's really an open source community doing it. And it's probably the oldest build system still in activity. It's been created in 2001, actually, so it's quite old. And the community is very active, regular releases. I'm going to talk more about that a bit later. So who's using Buildroot? Google is using Buildroot. They do Google Fiber in the US, and the boxes, they have an embedded Linux system, and they use Buildroot to produce it. Barco is a, international company doing visualization systems. Rockwell Collins, they work in the defense and aerospace industry, and they also use Buildroot, and they're even contributing to it. And we have many more. I just took like 3 examples. We also have a lot of processor vendors that are using Buildroot as their BSP, so they provide their customers a Buildroot that is specifically configured for their own architectures. So like Analog Devices for Blackfin, Imagination Technologies for MIPS, Marvell, Atmel for ARM, and there are several others. And also many hobbyists that do embedded Linux development on boards like Raspberry Pi or BeagleBone Black and so on find Buildroot really nice because it's easy and simple. So how do you get started with Buildroot? Well, you just grab it from the Git repo. Well, there are stable releases, of course, but it's probably easier with the Git repo. And then you fire make menu-config, and you have the well-known menu-config interface to configure all the different aspects of the embedded Linux system you're going to produce. So I'm going to go through pretty quickly on the different configuration aspects that are available. So first you need to select the architecture, and as you can see there are several of them that are supported, including like ARM64 or SuperH or Nios2 that are quite weird architectures, and all the more common ones are available. And then in this part you can also select more specific options specific to each architecture, like the type of processor and what type of floating point strategy and so on. There are some like build options where Buildroot is going to download the tarbles, how many things you do in parallel, whether you want to use Ccache and that kind of things. Another very important part is the toolchain, which cross-compiler you're going to use. And you have 2 options here. Either Buildroot can build its own cross-compiler, in which case it's going to build GCC and the C library and the build-utils and so on, and it supports userlibc, glibc, and eglibc as the different C libraries. Or the other option is to use what we call an external toolchain, where you already have a cross-compiler that's known to work really well for your architecture, and you can just tell Buildroot to use it. And the other advantage of using an external toolchain is that you don't have to pay the price of building the toolchain, which takes quite a while. So you save like maybe 20 minutes to 30 minutes of build time if you use an existing toolchain. Then you have a way of doing some system-wide configuration, like which init system you want to use, whether you want to use BusyBox as the init system, which is the default because that's very small, or if you want to use systemd or a more traditional system5 init. You can select how you want to handle /dev, like whether you want to use udev or devtmpfs. There are various solutions. And other, system-wide configuration options, like what's the root password and whether you want a shell to run on some serial port and so on. Then you can define which kernel should be built, like which version, whether it's come from a Git repository or whether there are patches, which configuration should be applied, so it can be given as a file or as a dev config. And we have support for the 2, probably most popular real-time extensions like RTAI and Xenomai, so it can be integrated easily in Buildroot as well. And then the most important part is definitely the target packages, what you're going to put in your root file system. That's where the highest value of the embedded Linux build systems is. And that's where we have more than 1,000 packages. So we have things like Qt4, 5, x.org, GTK, EFL. So that means that by simply selecting an option in the menu config, you can get Qt5 built for your target platform without having to worry on how you actually need to configure it and compile it and how to install all the stuff. We have things like Gstreamer, FFmpeg, many interpreted languages, many networking applications. We have, since Google Summer of Code last summer, we have OpenGL support for various platforms and many libraries and utilities. There are too many to name all of them, obviously. Another part of the configuration is which file system format you want to generate. So we support things like ext2, 3.4 of course, but also more embedded specific file systems like ubifs or gffs2 for flashes, or SquashFS for read-only file system. So this morning someone was asking during the lightning talk, I'm having like file system corruptions on Raspberry Pi for some museum exhibitions and so on. So typically a good answer would be do something with SquashFS, and Buildroot can by default generate a root file system that remains read-only. So if it's read-only, obviously you kind of limit the occurrence of file system corruptions. I'm going in the wrong directions. You can also build bootloaders. So depending on which architectures you use, the bootloader will be different, but we support grub, Linux, U-boot, Bearbox, and a bunch of platform-specific bootloaders. So really you define all the aspects of your embedded Linux system. There are also the possibility of building some native tools that are useful for development, but it's kind of a side thing. Here is an example configuration. So just like the Linux kernel, the configuration gets saved in a file named .config, which is just a text file that says for each option what's the value. So here is the configuration for the Raspberry Pi. So it's going to build a kernel for ARM platform with an external toolchain. It's going to include the Raspberry Pi firmware and userland, proprietary binaries, the I2C tools, and then the TV headend streaming server, and the Dropbear SSH server, and the light HTTPD web server. And just with this configuration, it's going to produce you directly an image that you can use on your Raspberry Pi. So to start the build, you run make, and that's the point where you drink 1 or 2 or 3 cups of coffee or tea, depending on your taste. And at the end of this process, in the output images directory, that's where the real stuff gets put at the end of the build process. You have the root file system image. So here I've selected both a tarball format and a UBI format, which is for some embedded system. You have the kernel image and the U-boot bootloader image. Of course, it completely depends on your configuration, but that's really what needs to be flashed or installed to your target system, like pushed to your SD card or flashed in some way to your embedded Linux platform. I'm going in the wrong direction again. So if you want to have a look at the build output of what Buildroot generates, it all goes in the output directory by default, but that can be changed using O equal to do out of tree build, exactly like the kernel. And output contains output build, where Buildroot is going to extract the source code for each and every component it's going to build. So for like GCC, BuzzyBox, and light HTTPD, and so on. And that's where it's going to build each of them. Output host is where Buildroot installs all the host utilities. So like when you build things for the target, you need things for the host. For example, the cross-compiler, but there are many other tools that you will need, so it's going to install them here. In output host user, the tuple of your architecture, so typically something like ARM, unknown, Linux, like GNU ABI, sysroot, it's where Buildroot is going to install all the headers and the libraries that have been built for the target. And it allows the cross-compiler to find them and build more libraries and more applications on top of the libraries that have been built previously. That's what allows to, solve the dependency tree. Output target, it's what contains almost the target root file system. So why almost? It's because since Buildroot does not run as root, we cannot really create completely the root file system. The permissions and the file ownership are wrong, but we fix that up later when we create the real images, so that this directory cannot be used directly as the root file system, but it's really almost like it. And then, as I said, output images where you find the final images that are interesting. So the build process is pretty simple. Of course, if you go into the details, it's a bit more complicated, but the overall overview of the build process is quite simple. Buildroot starts by copying what we call the root file system skeleton to the target directory. So the root file system skeleton is just like an empty root file system. It is just like etc and bin and lib, completely empty, just a bunch of config files in etc, and that's pretty much it. Then it takes care of the cross-compilation toolchain, and as I said, there are two solutions: either let Buildroot build your toolchain or use an external toolchain, and in both cases, Buildroot takes care of what's needed to either build it or like import the already existing toolchain. And then for each of the selected packages, it's going to first take care of its dependencies. So it's going to do this third step recursively for each of the packages. And for each of them, it's going to download the source code and potentially some patches, extract them, apply the patches, configure it, build the components, and install it. And it's going to install it in different locations depending on the specific component you're building. For target application and libraries, they are obviously going to be installed in output/target, so they end up in your root file system and show up in your target platform at the end. The target libraries also are installed in the sysroot so that they get seen by the cross-compiler when you build more application and more libraries, as I was saying. And in output host, that's where we install all the native libraries and applications, like the cross-compiler itself, but also more things like, I don't know, if you need Flex or Bison to build something, they are going to be installed in there. And finally, once that process is done for all the packages that you've selected, taking care of the dependencies and ordering the build properly, it's going to generate the root file system image and your system is ready to use. So here are two real-world examples of projects that I've done using Buildroot. So one of them was for a company making a device based on an ARM Atmel CPU, which was like 200 or 400 megahertz maybe, like 64 megs of RAM, so pretty limited. And in this device, it was used to like track things going on using GPS, RFID readers, GSM modem, Ethernet, and USB. And in the system, we had like we used a glibc toolchain pre-built, so we didn't have to spend time building it. A Linux kernel, BusyBox for the basic stuff, an SSH server and clients. We had the basic Qt library, not the graphical part, but all the core. And some more components like PPPD for GSM interaction and some special RFID library and other things. The Qt application that was really making the system do whatever it was designed for. And we generated a GFFS2 file system. And the file system was 11 megabytes in size with all these components. And it was actually using glibc, which could be made a little bit smaller if we used uselibc. And to build all that stuff, it was taking 10 minutes on a quad-core i7 build machine, which isn't like, it's good, but it's not exceptionally, enormous in terms of CPU power. Another one is a system that's based on x86, which is used for a vehicle navigation system that mainly runs an OpenGL application showing what's going on in the area. So here we used a glibc toolchain that was prepared with a tool called cross-toolng, which is specialized in the creation of cross-compilation toolchain, so that again, Buildroot doesn't have to spend the time to rebuild the toolchain over and over again. We used the grub bootloader, Linux kernel obviously, and BusyBox. It's kind of always the same thing. We had a large part of the x.org stack. And there was one interesting thing here is that this project was using an ATI card, which is proprietary driver for the OpenGL implementation. And those drivers were dependent on a very specific version of the kernel and a very specific version of x.org. And thanks to the fact that we're building everything from source, it's pretty easy to select very precisely which version of each component you want in the system, which sometimes is a little bit more complicated when you have binary distributions. Of course, you could use like an older Debian, but then everything is older. While here we can have everything recent except just the very specific libraries or version of the x.org server. So the flexibility of building from source is sometimes very useful. And then we had a bunch of libraries like ASA stuff and V4L and so on, and the OpenGL application. And in the end, the file system was 95 megabytes, which is quite huge. But if you look at what's made this size, there's actually 10 megs of app and 45 megs of the ATI driver. I don't know what they do exactly in their drivers and OpenGL implementation, but it's crazy. And this system was taking 27 minutes to build on the same build server quad-core i7. So it's pretty reasonable. I mean, of course, you need to drink a little bit of coffee, but not too much. So besides selecting the different packages, there are different ways you can customize the build because, well, packages are interesting, obviously, but possibly you need to add more configuration files or adjust things in the root file system, and there are different ways to do that. Buildroot provides what we call post-build and post-image scripts. So in the build process, which I can basically go back here, you can ask Buildroot to execute a script before point 4 and after point 4, which is respectively post-build and post-image. So before the image is created, you can like add more files in the root file system, adjust configuration files, remove things, and do whatever customization you want. And after the images are created, you can maybe bundle them together to create a firmware image update that will be pushed to your customers or whatever. That's one way. And we have another way, which is called the root file system overlay. It's kind of related. It's basically, you tell Buildroot, here is a directory that contains stuff, and once the build is done, just take this stuff and copy it inside the root file system. So you can put all your custom config files, custom init scripts, custom maybe even application or whatever in there, and it's gonna be part of the build and taken by Buildroot into the root file system. And the last way you can use to customize the build is by adding your own packages, either to package open source components that are not yet handled in Buildroot, or your own in-house components because you need to integrate your own libraries, your own applications into the build. And so I'm going to show quickly what it looks like to create a new package in Buildroot. So first of all, you have to make your package appear in the menu config interface. And here, thanks to the fact that we use the exact same code base as the kernel for the kconfig base, well, it's exactly the same as defining configuration options inside the kernel. So any person having a little bit of kernel development experience knows how to do that. If you don't have a kernel development experience, as you can see, it's pretty easy. So here I'm showing the libmicro HTTPD package. So basically, we're defining a config symbol and naming the option. That's what will appear in menu config. Define the dependencies. So here, this package has no specific dependencies except that the toolchain should provide thread support, a description, and then we have a little comment that says, hey, your toolchain doesn't have threads, so you can't enable libmicro HTTPD. Once this is done, and obviously this should be done in a directory that's named after the package, so package/libmicro/httpd/config.in. Once you've done that, you need to go to the upper level config.in, which includes all the config.ins for the different packages, and add a new include. So it's source and the name of the file we just created before. So that's the easy part. And then you need to describe actually how to build that package. So how to extract it, how to configure it, how to build it, how to install it. But it turns out that libmicro/HTTPD uses the autoconf and automake. So the way to build it and configure it is very standardized. So instead of repeating that for each and every package in Buildroot, you can use what we call a package infrastructure, which is named AutoTools package, and which is going to factorize all the gory details of building an AutoTools package and do all of that for you. So what we have to do here is just give a bunch of variables, values, the version of the component, where it can be downloaded from. We can also give the license. I'm going to get back to that later. We are saying that it should be installed to staging. This means that it's going to be installed both in the target and in the sysroot of the toolchain because it's a library. So if we want the cross-compiler to see that library for upcoming compilations, then we need to tell that. And then we can pass configuration options to the configure script. I've stripped down the real thing because here we handle things in the real Buildroot. We handle things like optional SSL support, for example. So if we see that we have OpenSSL available, we pass one more option to tell libmicro/HTTPD, please enable SSL support. And that's all what you need. That will create the package. It will automatically download the tarball, extract it, it will configure it, build it, install it. So that's all what you need for AutoTools packages. So we have different package infrastructures depending on the type of package you want to create. If your component uses AutoTools, it's AutoTools package, as I've shown. If your component uses CMake, then we have CMake package. If your component is a Python module using either distutils or setup tools, we have Python package recently that I've recently integrated. And then for all the rest, we have an infrastructure called generic package where you have to do a little bit more work because you have to explicitly say what should happen to configure and build the package. And what's coming is infrastructure for Perl and Lua packages. So we're progressively improving those package infrastructures to make it simpler to package Perl and Lua stuff. Beyond building the system itself that you run on your target platform, another thing that Buildroot provides is what we call a legal infrastructure. So as you've seen in the example, the libmicro/HTTP package is associated with licensing information, like which license and which file describes the license. And we have that for not yet all of the packages, because that's something we've introduced like less than a year ago. But it's growing, and I think more than half of our packages have licensing information. So what we can do is that when you run make legal info, it's going to extract the legal information for all the packages that you've selected in your embedded Linux system, and it's going to provide you a licensing manifest in a CSV format saying all the components, all their version, all their licenses, so that you can very easily do licensing compliance. It's going to store in one directory the license for all the different components and the source code for all the different components. So if all of this is right, technically you can just take all that stuff, put that up on your website, and you should normally be compliant with the open source licenses that you use in your system. At least that's the idea. So I think that's a pretty cool feature for companies doing embedded Linux systems. It uses directly the embedded Linux build system tool to help in doing license compliance. It can also do dependency graphing, so that's very interesting to understand why a particular component has been taken into the build. So you do make graph depends, and it generates a PDF that looks like that for I think it's the Raspberry Pi system, that's the configuration I was showing before. So I'm not sure you can read, but we can see that there is BuzzyBox, it's building the kernel, and the kernel needs a bunch of things. It's building light HTTPD, which needs some other stuff, and so on and so on. So we can very easily understand why a component has been brought into the build. Another thing that comes with Buildroot are dev configs. So it's pretty much like the kernel ones. Dev configs are configurations for popular platforms. And in Buildroot, we've decided to have configuration that build a minimal system for the platform. So for example, we have configuration for the Raspberry Pi, for the BeagleBone, for the QB board, for Panda board, for many Atmel boards, Freescale boards, and also for many QEMU configurations, so that you can like experiment with Buildroot and run things in QEMU ARM, QEMU MIPS, QEMU Spark, and we have many of them, like tens of them. And it builds the most minimal system possible. So like the 2 megs root file system I was explaining before, it is just the C library and BuzzyBox, and that's it. And then on top of that, you can add more packages depending on what you want to do with your system. Some people will use their Raspberry Pi to do a media center. Some other people will use it to maybe monitor the temperature in their house or something. So the set of packages will depend from one usage to the other. But at least those dev configs, they build the right kernel, the right bootloader, select the right architecture options, and so on, and give you a system that is known to boot on this platform. So to use them, you just do make blah blah dev config. So like make Raspberry Pi dev config. It's going to load that default configuration, and you start the build by running make, and it's going to produce you a system that runs on your Raspberry Pi. As I said before, Buildroot is an active project. It has had a quite hectic history with periods of without any maintainer, things going quite bad and so on. But since 5 years now, it's since beginning of 2009, we have a maintainer, Peter Korsgaard, who lives in Belgium, and he is the gatekeeper for all the changes going into Buildroot. So a bit like in the Linux kernel, there's only one person having commit access to the Git repository. We review patches on a mailing list and so on. So since he has been leading the project, we have published releases every 3 months, very regularly. They have always been in time, so it's pretty good for users to know that, well, every 3 months we care about stability. So we basically have 2 months of development and then 1 month for bug fixing. We have a growing number of contributors. These days we have between 35 and 40 different contributors each month that have patches integrated into the tree. So we have, in fact, many more contributors sending patches, but for the patches that are accepted, it's like 30, 40 people each month. Mailing list activity is also showing that the project is gaining interest, like between 1,500 and 2,000 emails a month, and it's growing. And the number of packages is also growing. So as you've seen, it's been flat for a while. Which was several years ago, because we have had a huge period of cleanup when the new maintainer was appointed, and we cleaned up a lot of things, like rewrote most of it. And now we are in a phase where we can benefit from the cleanup and add many more packages, which is what's happening right now. And we have physical meetings twice a year. So here it was last year, February, in Brussels, in the Google offices, because since they use Buildroot, they are nice enough to provide us meeting rooms. And so we have like developer meetings, and we're going to have again one in Google offices in Brussels just next month, in early February. So if you want to try out Buildroot, there is a pretty good documentation, as I said, that's available, especially describing how to add packages. It's very describe things with a lot of details. And like any other good open source project, we have, as I said, the ugly logo, but we also have the mailing list, the RC channel, a bug tracker. I'm tempted to think that our community is quite friendly and welcoming. I mean, since it's a tool that's pretty easy, a lot of the people that come in are usually newcomers in the embedded Linux space, and we try to be nice with them and explain them how things work and so on. And there are also companies offering commercial support around Buildroot. So to conclude and leave some time for the questions, I have like 8 minutes. I think it's a nice tool, and because it uses well-known technologies and languages, you don't have to learn some funky language to use it, and the community is active and friendly. It's simple. If you want to understand what Buildroot does, it's just a few hundreds of lines of code to understand. They are not the easiest part of Buildroot indeed, but the core of the package infrastructure is really just a few hundred lines of code. So even newcomers, after just a few months of like playing around with Buildroot, they are able to provide patches that touch the core of Buildroot because it remains simple. And that's something that is really key in the project. Whenever we have requests from users for new features, we always try to see whether the request for that feature fits in the simple model that we want to keep, and whether it shouldn't be handled as like an external script that should be called or something like that, to avoid cluttering the tool with more and more use cases that are being handled in bizarre ways. So we try to have like one way to do things and only one, and not clutter with many features. So sometimes it's a little bit to find the right balance here. But I guess it's a challenge that many open source projects are facing. So it's really easy to get started. In just an hour, you can have built your file system for the Raspberry Pi or any other board that's supported and run it on your platform. So it's really easy. And it's pretty efficient. The build times are quite reasonable, as I've shown. Just use a reasonable machine. If you use like VirtualBox on a very crappy machine, of course it's going to take a while. But other than that, it's pretty efficient. Okay, I guess it's time for questions. If you ask questions, please speak clearly and loudly. I'm not a native speaker, so if you like grumble, I'm not going to understand. Yes, please.
I wanted to ask how many lines of configuration you used. It showed 2 examples, and I'm wondering how many lines of configuration did each of those 2 examples require?
So the true real world, so the question is how many lines of configuration each of the real world examples I've shown required? Is that your question?
Yes.
So if you take a .config, it contains many lines of code because it has the value for each option, just like in the Linux kernel. The one I've shown is the result of running make save devconfig, which creates a devconfig file that only contains the option for which you've chosen the non-default value. Okay, so that's what makes them relatively short. For those systems that I've shown, basically just count the number of words, more or less. Like the toolchain is going to be one option, Linux kernel is going to be maybe 5, 6 to select the right version and config, BusyBox is one option, Drawbear is one, Qt is a bunch more, like maybe 5, 10 options. Each of zlib, libxml2, logrotate, ppbds trace are going to be one option each. The Qt application is one. So as you can see, it's going to be maybe like, I don't know, 30, 40 lines or something like that. And this one is a little bit bigger because it has x.org, but it's going to be maybe 60, 70 lines of code of config, but you don't write it. I mean, nobody writes, well, I do write them from time to time, but nobody writes that thing. It's generated by menu config. So you just navigate in the menus here and select whatever you want, just like when you configure your kernel, and you don't have to worry about it.
list for things that newcomers should target, like if they want to get into developing a project?
Okay, so the question is, well, first, thanks for thinking the tool is great for newcomers. And the question is there a to-do list? Yes, there are different opportunities for newcomers to do things. We have a wiki on linux.org for Buildroot, and it has a small to-do list. It's not that big, but it's, well, quite, it has a few things. We have reports from the previous meetings that always list a huge number of things to do and report the discussion that we had. So for newcomers, it's a good way of like seeing what are the topics currently in discussion and maybe jump in some of the topics. And then we have all the patches are recorded in a tool called Patchwork, and it's anybody can look at them and maybe grab one of the patch, test it, review it, and give feedback. That's something we're missing quite a lot at the moment, review of patches. And then we also have a bug tracker, but it's probably a bit trickier for newcomers to directly tackle bugs. And then, as usual, just scratch your own itch and build a root file system for your device, do things, and you'll probably figure out that something should be updated or improved and things like that. Other questions? Yes, please.
The recipes for the individual packages look very much like ports. Like the BSD port system, it's a fragment of a makefile with an include. I'm wondering if you can't steal from the various port systems or Gentoo with respect to building a new package that is currently in the system.
So I'm being told that the recipes, like the makefiles, look very similar to the ones of the FreeBSD ports or Gentoo recipes and so on. Yes, and that's the same for other embedded Linux build systems. I mean, if you look at Yocto, Open Embedded, PTXDist, and so on, they all have this kind of recipe language. And we don't directly reuse what the others are doing, as we don't copy-paste what they're doing, but we look a lot at what others are doing. And I believe they're doing the same because I know some other build systems are reusing some of the patches that we have and so on. So there's a lot of reuse, but it's not direct reuse because the syntax is different. The variable names are different and so on, but there is a lot of reuse. I mean, I'm currently working on improving the Python cross-compilation support. I'm talking with a guy from Canonical doing work on Python in Ubuntu, and I'm interacting with other build systems, also cross-compiling Python. So we are interacting with other projects, but it's much more difficult to directly reuse recipes.
Just about toolchains. Internal or external? I mean, I'm sitting here now, sort of building a sample, and of course it's basically growing in place with GCC and Linux. I think it's going to take a little while. It's going to take a little more than 20 minutes. So is it better to just go and use the external toolchains in preference to internal?
So the question is between internal and external, what should I choose? Internal seems to take quite a while to build. So yes, indeed, internal is going to build binutils, then going to build all the dependencies of GCC, then going to build GCC like 3 times and build the C library, so it takes a while. On my side, I mainly use external toolchains. Some of them I produce with Buildroot itself. So I use Buildroot once to build a toolchain, and only that. I keep a copy of it somewhere, and then I use that toolchain as an external toolchain in Buildroot. And I have a good number of them for each of the architectures that I care about. So that's typically the way I do things. But I know some people stick with the internal toolchain because they don't rebuild it every day. You build it once and then you do more modification to your configuration, and only maybe at night you're going to restart the build from scratch.
There are times when if you change the configuration, you'll end up rebuilding the toolchain.
Of course, yes. Whenever you do a make clean, it's going to rebuild everything. So you'll have to rebuild the toolchain again. So Buildroot has a very simple approach to configuration changes. It simply doesn't track them. So when you do a configuration change, if you add a package, it's going to notice because, well, it's not installed, so it should be installed. But if you remove a package from the configuration, it's not going to remove it from your target root file system. Other systems do that. We don't do it simply because it would add too much complexity to the core. Last question in the back.
Can I use Buildroot without a network connection?
So the question is, can I use Buildroot without a network connection? I will say yes, but at some point you will need a network connection to grab the tarbles once. But we have a lot of mechanisms to help you do offline builds. So we have make source, which is going not to trigger the build, but only the downloads of each of the tarbles that are needed. We have make external depths, which is going to spit out the list of the tarbles that you need to do an offline build. We store all of the tarball in a specific location, but you can also give what we call a primary site, which is an HTTP server where Buildroot will fetch tarballs instead of going to the web. So like in your company, you can have one internal HTTP server with all the tarballs that you care about and be completely isolated from the rest of the world. So that's a pretty common requirement in some companies. So I think we support that quite well. Well,
Okay.
Thank you very much for your attention.